Welcome. We are discussing symmetry groups. Group is a set of elements with an operation defined for adding or multiplying the group elements, and under the operation these elements satisfy certain properties. First is called closure. So, if you take any two elements and if you do this addition or multiplication operation, you end up with an element which is also in the same set. The second one is known as associativity. It says that if you have three elements A, B, C belonging to a group, whether you multiply B, C first and then left multiply A to it, or you multiply A, B and left multiply that to C, does not matter. So, this is known as associativity. And then there is a unit element which if you multiply with all the other group elements, you end up with the same element, and there is also an inverse element. For every element there is an inverse element which if you multiply with the element you will get the unit element. So, if any set of elements under some given operation, multiplication or addition, it is called group addition or group multiplication, obeys these four properties, then we call that as a group. Now, we also defined what is known as a symmetry group. What is a symmetry group? So, we considered an equilateral triangle and we defined symmetry operations, and those operations are about the CFG. For example, you can rotate 120 degrees. So, 120, 240 and 360 is basically equivalent to 0 degree rotation. So, those are three, and then we also had reflection operations. So, we defined some three lines which pass through CFG and which are perpendicular bisectors of the opposite side about which you reflect, for example. So, we defined this I think as F, G and H. So, the operations, the three rotation operations and the three reflection operations, and under the combination, for example, you do one rotation, you follow it by another rotation, or you do one rotation and then you do a reflection, right. So, that is the combination is a group. So, that we saw last time, and there is another way to represent the same group, and that is as follows. So, the elements of the group can also be represented by matrices. Of course, first is the I operator, which is the unit element, which is nothing but 1 0 0 1. The second one is A, which is 120 degree rotation, which is given by, and the third one is 240 degree rotation, and this is given by, and then the reflection operation F is defined by, okay. And because the reflection operation F takes the x point to minus x, but it leaves y unchanged. I mean that is what this operator is. And the other two reflections G and H are similarly defined. G is and H operator is defined like this. Now, all these 6 elements, so you can make a group table like we did last time. So, you can call I, A, B, F, G, H and I, A, B, F, G, H. You will see that all the elements are I, A, B, F, G, H only, and I happens to be the unit element, and for every element you can find out the inverse element and these operations, which are basically if you consider IAB, FG, H as these matrices, the multiplication operation, the group multiplication operation is nothing but the matrix multiplication. So, under the matrix multiplication you will get the properties, and notice that because these are matrix multiplication, they are generally not commutative. A into B does not necessarily mean B into A. If in a group it happens to be so, such a group is called abelian, and if it is not, it's non-abelian. So this is the symmetry So, these are the symmetry elements of equilateral triangle and it forms a group. So, this is known as a symmetry group. So, this is the symmetry group for an equilateral triangle. With this idea in mind, we now want to define what is known as the point group symmetry of a crystal, because remember we are doing all this exercise to understand the Neumann's principle, which says that the physical property of a given crystal should include the point group symmetry of that crystal. Okay. So, we need to understand what is the point group symmetry, and then we also need to understand how we define the symmetry of any given property. Okay. To understand point group symmetry, let us start with what is the what is known as a lattice. So, what is a lattice? Lattice, okay, is basically points in space which are periodic. Okay. So, the periodic array of points in space is known as lattice, and if with every lattice you associate certain atoms or molecules, and the atoms or molecules that you associate is known as a motif. Okay. So, if you associate, for example, I might have this as my lattice, okay, and this continues in both the directions, both x and y directions, this is infinite, it continues. And if I associate, for example, with every point a set of atoms, right, suppose if I repeat this, so everywhere I do this. Okay, so this will be called the motif, and the lattice plus motif actually makes the crystal structure. So, this crystal structure then can be explained in terms of what is known as a unit cell, right. So, there are many different unit cells. For example, the simple cubic unit cell is the one which will be a box like this, a cube, and which has atoms probably at every point, right. So, note that this could be an atom, this could be a molecule, so anything that you can put, but for simplicity's sake I am just taking atoms and I am putting at the lattice position. So, this is a unit cell. Now, like we did in the case of equilateral triangle, you can take a shape like this and define certain symmetry operations. Those basically form the symmetry elements. What are the symmetry elements? There are many, but we are going to define what is known as the point group. So, there are certain symmetry elements that we will discuss. So, what are those symmetry elements? One is known as center of symmetry, or it is also known as inversion. This what we do, for example, you take the center of this unit cell, and suppose you had the x, y, z axis, you invert all of them, x goes to minus x, y goes to minus y, z goes to minus z. So, x comma y comma z goes to minus x minus y minus z. Okay. So, this is a symmetry operation. Okay. This is known as either inversion or center of symmetry. So, this is one symmetry operation. So, it is a symmetry element. The second symmetry operation that we want to define is known as a mirror plane. Okay. So, what is a mirror plane? So, suppose you have a set of elements like this, right, something like this, right. Suppose if I take a plane about which I mirror this, right. So, this is a mirror plane, and so this is a symmetry operation. So, mirror plane is a symmetry operation. So, center of inversion is one, mirror plane is another. Then you can have rotation, and the rotation could be one fold, two fold, three fold, four fold, or six fold. What is this fold mean? If it is n fold, you rotate by 2 pi by n. that is what n-fold means. So, 2-fold means you rotate 2 pi by 2, so that is pi, that is 180 degree rotation. 3-fold means 2 pi by 3, and so 2 pi is 360 by 3 is 120. So, in the case of equilateral triangle what we had is basically a 3-fold. 4-fold means 90 degree rotation, and 6-fold means a 60 degree rotation. 1-fold basically means 2 pi rotation, which means you do not rotate it at all, 360 degrees there is no rotation. Then there is what is known as inversion, and those are 1-fold, 2-fold, 3-fold, 4-fold or 6-fold. So, this is rotation and this is inversion. In this case what we do is that we do a rotation, right, of whatever 2 pi by n rotation, and then we choose a point on the rotation axis, choose a point on the rotation axis and do an inversion about that point. Okay. Now, the inversion, so let me write it here, inversion, mirror plane and n-fold rotation and n-fold inversion, these are symmetry elements, they form a group. So, that is known as a symmetry group, and this is known as a point group symmetry, and the name comes from the fact that when you combine these operations, all these operations can be thought of as being done about a point, right. In other words, we are looking at symmetry operations which do not involve any translation. So, we are lattice is repeating the same sort of point structure in space indefinitely in all 3 dimensions, right. So, that is how you get a lattice. So, that is a mathematical concept, and with each lattice point if you associate a motif, then you get what is known as a crystal structure, and the crystal structure can be described in terms of unit cells. Now, when we are thinking about the point group symmetry, we are thinking about this unit cell and sort of what are the macroscopic symmetry operations that you can do on them. So, those are the symmetry elements, and I consider only those symmetry elements which can be thought of to be carried out about a point. For example, you can have a point, you can have an axis through the point about which you will do rotation, you can have a plane which consists of that point about which you will do reflection, and about the point you will do inversion. So, everything is with respect to a specific point, which means the translation is not something that we worry about. So, the group that you form with these symmetry elements for the unit cell is known as a point group symmetry. So, we have defined one part of the Neumann's theorem which says that the symmetry of any given property of a crystal should include its point group symmetry. So, now we know what is a point group symmetry. What is a point group symmetry? These are symmetry operations which are inversion, mirror plane, n-fold rotation and n-fold inversion, and they form a group. So, that is the point group symmetry. For example, if you think of the simple cubic unit cell that I described a while back. So, the one of the important point group symmetries of this cube is that it has a 3-fold rotation about 4 axes, and those 4 axes are the diagonal ones, from here to here, from here to here, and from here to here, and from here to here. So, there are 4 of them, and you have 3-fold axis about these 4 axes. I mean, that is one of the important symmetries that this cube has, for example, and in the case of FCC it is easier to see. So, that will be basically the 1-1-1 plane. So, these are the kind of operations. So, these are the kind of symmetries that exist with respect to the macroscopic symmetry operations on a unit cell, and that forms a group, and that is known as the point group symmetry. So, we know what symmetry is. Symmetry is any operation that leaves the object unchanged. It could be a mathematical object, it could be a physical object, it could be a geometrical object, and the operation could be a mathematical operation or a geometric operation, and under that operation if the object remains unchanged, then we call that as symmetry. And the element, the symmetry can be described. For example, we decided to describe the symmetry of the triangular equilateral triangle using rotation matrices and reflection matrices. So, you can use matrices to represent. So, they basically become these symmetry elements, because these operations form a group when they are combined with each other. For example, you do an inversion and then you do a rotation, you do a rotation and then you do a mirror. So, these operations combine together, so that combination. So, if you think of these group elements as matrices, these are just matrix multiplication. So, a way of combining these matrices, then they form a group. So, that is the point group symmetry, because we are only considering those symmetry elements which can be thought of to be carried out about a point with respect to the unit cell. Okay, so we consider some point in the unit cell about which we do all these operations. So, it is known as point group symmetry, and so we now have an idea of what it means to say that the point group symmetry. Okay. So, now this the property should have a symmetry which includes the point group symmetry. So, what does it mean to say that the property has some symmetry? Okay. So, that is what we will discuss in the next part of this lecture. Thank you.